Hi, my name is Cole Hartley, and this video will serve as an introduction to um, new series that I would like to do on my senior project. My senior project is a personal pick and place machine. This presentation will mainly go over the electrical side of it. So a little bit about our team. I'm the leader of the electrical sub team with one other electrical engineer. We have uh, two mechanical engineers and a engineering technology major on the mechanical team. So the purpose of this video, as mentioned earlier, is to just give insight to the electrical side of it, as well as emphasize me and my team's just skill set and our contributions. So before I move on, I would like to go over what a pick and place machine is for maybe anybody that doesn't know. So a pick and place machine is typically a four-axis machine that picks up electrical components and places them on a printed circuit board. These components are typically on the uh, magnitude of a millimeter, even less, a tenth of a millimeter. Uh, so you can imagine how hard that is to do by hand. So these machines remove the need for hand placements, thus reducing human error and therefore increasing production. These systems are also fully autonomous, meaning um, you really only need one user input, maybe a little bit of calibration, but then you're set to go. So moving on, we have our full machine overview. On the left, we have our main goals, and then we have our objectives, and in the middle, I've got whether or not it is impossible or possible. Um, Spoiler, they are all possible. So starting with compact design, we would like for it to be able to fit on a desk. Think maybe a small 3D printer. We would like for it to be lightweight. I think a great goal is around 25 to 30 pounds, which is quite possible with some of the 3D printing that we're doing, as well as our aluminum frame. This being said, it should have an integrated power supply for it to be fully portable. So no reason to carry around a full-size PSU um, or anything like that. And we're also using parts from an Ender 3 V2, which is a small scale 3D printer, as mentioned earlier. So you can kind of put that into perspective. Our second goal is high precision. So this will be done with our four-axis movement with millimeter microstepping and a camera vision system as well for PCB recognition and calibration, stuff like that. Our third goal is high efficiency. So we plan on training an error detection AI to detect and handle these errors being misplacements and incorrect component pickups. So uh, having this in place will reduce the user having to backtrack and find out what was wrong, or maybe they never even find out what's wrong and it just gets implemented into the board anyways, and you don't really know that it's a problem until you turn it on and maybe something pops. Uh, Secondly, we would like to incorporate automatic feeders. Automatic feeders reduce just downtime. The user no longer has to manually place component strips and calibrate the machine. The machine will know where the strips are, and the machine will automatically spit out new components. We will also implement custom actuator scripting. This scripting will be optimized for just quick responses to what the machine wants. So if the machine wants a new component, then the script will, boom, new component. Lastly is our ease of use and accessibility. This is all possible through OpenPNP's UI. The user is really only responsible for a placement file with OpenPNP, which is great. And everything that we are implementing is very modifiable because it is open source. So in this presentation, I would really like to go over the high precision systems and high efficiency systems as it is in tune with what the electrical team is working on. Before we get on to those systems, I would like to acknowledge that there are pick and place machines on the market readily available now, but they are quite expensive and will not have all the features that ours will. So starting with the one in the top left, it is non-autonomous and still coming in at $530. Non-autonomous meaning it has no program, it has no motors, you still have to move it by hand. In the top right is the more advanced out of the bunch. It has the automatic feeders, it has the programming, it has the motors, but it is $3,000, which is quite a bit for maybe a hobbyist, which is kind of the target audience with something like this. And then coming around in the middle is the Lumen PNP version 4. This is a great pick and place machine for any hobbyist. It's got a great community and very well supported, but it is still $2,000. Uh, our pick and place machine will incorporate all of the features that these pick and place machines have, plus our AI integration, and it will optimize construction costs, making it cheaper through the use of 3D printed parts and off the shelf pieces, mainly from like Amazon, stuff like that. We'll see more of that probably in the budget and parts list. So moving on to our machine precision systems, we have this will go over our X, Y, Z, and A movement, our camera vision system, and our component pick and place assembly. So starting off with our hardware, we have the TinyG motion controller. TinyG is mainly found in CNC machines, but through research and looking at the data sheet, it's well equipped for a pick and place machine. This is because of its 4 integrated stepper motor drivers. It has micro stepping capabilities up to 16. The firmware is open and customizable, which makes it great for calibrating on a do-it-yourself project. And it supports third order S-curve motion planning, which is calculations for the velocity, acceleration, and jerk, which just makes everything smooth out, which is very important for moving around very small components. You don't want them to fly around or anything like that. We'll be using a Raspberry Pi high quality camera. This camera is great for um, getting down to those like millimeter captures. Has 1080p resolution. We will be using it for feedback for fiducial and component recognition, which are, like I said, on the scope of a millimeter, just about, even less. I also put on here additional workspace LED. This will be a separate subsystem that will incorporate just to light up the space and make sure that we are capturing or that we are getting good captures. Moving on, we have our NEMA 17 motors that we will be using for the X, Y, and Z axis, and our NEMA 8 motors that we'll be using for the A axis, which is the rotational axis for our pick and place head. These motors are fantastic. They have 200 steps per revolution, a step degree of 1.8 degrees. They are also low current consumption in our configuration. Next, we have our vacuum pump and vacuum release solenoid. These are part of our pick and place assembly. The vacuum pump is cheap and simple from Amazon, but it does the job and provides quick vacuum activation. And our vacuum release solenoid will provide smooth vacuum release. Moving on to our software specifications, we will be using OpenBMP as previously mentioned. OpenBMP is a machine operation program specific to pick and place machines. It's responsible for the G code generation and the machine tasking as well. So in our machine efficiency systems, this will cover our AI integration, our open software application, and custom scripting. For our hardware specs, we start with the NVIDIA Jetson Nano. So the NVIDIA Jetson Nano is a single board computer, and it will be responsible for running all of our software. And Yes, as it sounds, the machine will have its own computer on board. This is necessary because of its GPU. This GPU needs to be used for training and tasking the air detection AI. It also has a strong benefit of processing our live camera footage quickly. Our automatic component feeder um, just reduces downtime and reduces manual intervention. For our software specs, we're going to be using OpenCV. OpenCV is a software that is used to train error and detection AI. It's quite popular nowadays. Our specific model will be used to detect errors and alert the user, preventing those errors from being part of the final assembly. We got OpenPNP again. This will control our automation of the machine once properly scripted and set up. Automation is key to efficiency. Uh, Robots are just much quicker than we are. So once we get that scripted and set up, it will improve efficiency of PCB construction by a lot. Lastly, we'll be using Python to program scripts for the actuators and feeders. These actuators and feeders are, the LED, the vacuum and release solenoid, the automatic feeders, as mentioned, and a few other things as well. So this leads into our procedural testing for hardware systems. I thought I'd just include this because I do plan on making a few videos just going over some of my testing stuff just for research purposes and just documentation. So my first step is analyzing my schematic. So I would like to fully understand the requirements for this subsystem. What are the inputs? What are the outputs? By doing so, we gain, you see it up above the arrow, is the fundamentals. So once we have the fundamentals of what the subsystem is supposed to be doing, we can move on to characteristics data and bench testing. So here we're going to ensure that the power readings are within range for the system. So whether that be, current rating, whether the voltages come back correctly, um, these just need to be solid before we move on, just for safety reasons, as you can see up on top. During this phase, I like to stress test and analyze this data, see where this component kind of lies. Can it be pushed harder? Do I need to find another workaround? A great example of this is the power distribution system. Uh, so we are using just a single 24-volt power supply, and we need to provide multiple voltages from 24 to 12 to 5. Um, so we need to make sure that those voltages reach their destination with enough current for proper system operation. From here, we move on to our software and hardware integration testing. So this begins with establishing communication with our software and firmware. Once that has been established, we're going to run simple scripts, for example, just an on and off script. This is crucial because we need to ensure that the basic system integration is successful and seamless, and that the power supply during these systems integration is sufficient. Uh, are the hardware components receiving these signals correctly? Once these initial tests are completed and we have um, found that the systems are compatible and that they are working together, we move into ideal system integration. So in this step, we're going to verify that the two systems perform their intended duties as if they were executing a real task, but not yet fully involved into the machine. So this is just taking this subsystem and giving it the script that it would be given if it was the full machine's operation. So during this test, we're going to check and see if the system completes its assigned task without errors or interruption. And If that comes back green, then we will optimize the precision and timing in these integration actions. I think a great example of this is going to be our servo motor rotation calibration. Um, in our auto feeder setup, we are going to use servo motors to essentially push our gear back and forth. This gear is going to roll the tape, the component tape, um, and essentially refill this auto feeder. So we need to make sure that the servo motor is going to that exact 90 degrees and back to 0 degrees. Our procedural testing for software and firmware systems, as you can see, the software and hardware integration testing is essentially the same for both of these. So we will just cover the bit in yellow. So starting with our program function, we are going to review the software specifications and the system requirements to understand the expected behavior of the machine. What would this script produce? So this would give us the fundamentals to move forward into testing this script on our hardware. So then we can start writing and testing the individual parts of the system, debugging as needed. This is our individual module and testing section. Once we get to this position, then we know the per unit function, right? So for example, uh, ensuring that the GPIO pin, the general purpose input output pin, is receiving that high signal, or that our I squared C um, communication is correct. So once that is set up and successful, we can start moving into our software hardware. We can start sending those signals, that data, to our hardware. Finally, we have our up-to-date as of February 22nd, 2025, our up-to-date parts list and budget. So I really just added this for if anybody wanted to kind of like follow along, they kind of see what all we are using electrically. I'm sure I can ask the mechanical team for their budget and parts list if anybody wanted it. Um, I think we're very lucky to have some of these parts provided by not only the team, but by our mentor, Dr. Tariq Yusuf. I would also like to acknowledge the fact that the electrical sub-team of our project applied and got funding for our project through the Office of Undergraduate Research. We won a lump sum of $750. So very grateful for that as we move forward. So up to come, I would like to continue the series, of course. I'm very passionate about it. I would like to document some of my testing procedures, as I mentioned before. I would also like to document certain milestones, such as, um, like motor movement and certain subsystems working, like, for example, the vacuum system. That'd be awesome. If you guys have any requests or comments, please let me know. Or maybe questions as well. Uh, Thank you.